Okay, next talk. We're also staying in the realm of TMDs at high fields, right? Our speaker is Dganit Meidan. What is your
so SPMS at Paris-Saclay.
SPMS Paris-Saclay. She'll be talking about signatures, control of nodal superconductors.
Yeah, so hi everyone. I'd like to start by thanking the organizers for the wonderful conference. Present this work here. And also thank all the speakers of this session, which basically gave half my lecture now, so I can kind of go quickly. I'll go to lunch quicker. So I'd like to talk about a nodal superconducting phase in monolayer TMDs, and especially signatures of that phase and potential ways of controlling it. Yes. And so this is a work done with us at the Hebrew University, ex-postdoc of mine, Université Paris-Saclay, who's now at Christ University, and my PhD student, Dganit Meidan, at Dganit Meidan University. And there's some Altem students here at SPMS, sitting also in the audience. He's doing some related work to this as well. Good. So, nodal superconductors were mentioned, but maybe just to kind of remind everyone that gapless phases, just like gapped phases, have topological classification to them. And the idea is that these nodal points we can interpret as some kind of momentum space point defects. And they have a stability who's guaranteed by a conservation of a topological invariant, just like in the case of gapped system. And so we can understand also that this kind of gives them a stability to these nodal phases. I'd like, however, to advocate for an alternative point of view for like the stability of these nodal phases, which again is well known. And so that is that we can kind of understand gapless topological phases in some dimension D in terms of concatenating topologically gapped phases in one, D-1. Right, and so the most common example, of course, is graphene. So we have just the regular type binding of graphene here, and right, and so if we kind of consider this system as like open boundary conditions in the system, yeah, I don't know if you see the pointer. So if we kind of keep open boundary conditions in the zigzag direction and kind of have periodic boundary conditions in the armchair direction, then we can think about this as an effective 1D Hamiltonian, which is kind of tuned by the momentum. Yeah. Okay. Yeah. So then we can think about this 2D system as just a 1D or a family of 1D Hamiltonians tuned by some K number. And so if you look at this resulting system, you kind of quickly realize that this is essentially an SSH model, just like the different hopping between intracell, and intercell. And so as we change, this tuning, this tuning parameter, in this case, Ky, we go between a set of Hamiltonians where we are in the trivial SSH phase to a set of Hamiltonians where we are in the topological SSH phase, and this kind of gives rise to this flat band, which is typical of these nodal phases. Yeah, and that flat band is, of course, observed in zigzag and graphene. In fact, it's rather general. That's another comment, maybe, to say that it's not specifically just in the zigzag direction. It's in fact present at any direction, except for the special phase of armchair. Of course, these edge states decay more into the bulk as we go away from the zigzag, but it's still robust. Okay. But today is not going to be about graphene. It's about transitional metal deep polycombinator TMDs. So this was already presented, and we're all now experts. And I'll say that I'll be focusing on this class of material. So clearly depending on this lattice arrangements, there are different symmetries of the system. I'll be concentrating on this 2H or 1H arrangement, where the system looks like a hexagonal lattice from the top view, with AB sublattice symmetry breaking, and that corresponds to the lattice structure of the selenite and molybdenum sulfide as we heard of it. And this already was presented as well. So now what we have is an inversion breaking in the system, and that inversion introduces some effective magnetic fields. So it means that the electrons experience in-plane fields, and then those instead give rise to an effective spin polarization in the out-of-plane direction. And so that is this Ising spin orbit coupling. And again, as Lena was already mentioning, the remaining symmetries of this system essentially completely constrain the form of this spin orbit coupling. And so it has this threefold symmetry. And so importantly, it kind of works very strongly the Fermi surfaces along the gamma K line. So there's this huge spin orbit splitting in the gamma K line. However, it exactly vanishes in the gamma M line. And so that is the structure. These plots, again, were already mentioned, so I'll kind of skim over them, but just to say that these monolayers are superconducting. And this, again, was mentioned that they have a very strong stability to in-plane magnetic field. And that kind of, again, can be understood very naively in terms of the presence of Ising spin orbit coupling. So typically, in a usual superconductor with no special Ising spin orbit coupling, the magnetic field polarizes the Cooper pairs and therefore breaks the pairs. And so that occurs when the field is approximately of the same size as the order parameter in the correct units. But what we have here is that so here, because the Cooper pairs have their spins very much pinned to the out of plane direction by a very large Ising spin orbit field. Actually, the in-plane field does very little to kind of tilt them out of this plane, and so then one has to overcome a much larger energy difference to kind of break it, so that it claims kind of huge magnetic fields. And so I'd like to focus on the physics around the gamma point, also because Carissa is telling us that there's not enough theoretical works on this limit, so let me instead focus exactly on that. And so what is expected to happen actually is that as we increase magnetic field beyond this Pauli limit, the system could develop into a nodal phase. And again, this is kind of, one can understand quite simply because, as I was saying before, let's say for Cooper pairs along the gamma K line, sorry, the Ising spin orbit pins these Cooper pairs in the out of plane, and so the magnetic field in plane does very little to kind of break the Cooper pairs. However, we have these special directions, this gamma M directions, where there is no Ising spin orbit coupling. And so as we increase magnetic field, those Cooper pairs would start to break. And so that gives rise to six pairs of nodal points that appear along this gamma M direction. As far as experimentally seeing this, well, there's some evidence of a six-fold dependence of the gap structure. It's seen in magnetic fields. This is an neoblue selenite. In other materials, this we've seen already. So some appearance of some density of states at edges or step edges in a different material, but again, evidence of a nodal, potentially a nodal phase. And a V-shaped gap would be also maybe an indication of the same physics. Okay, so okay. So just in terms of topological properties or how we can understand these. So clearly, I was talking about an in-plane magnetic field. There's no time reversal symmetry. However, there's an emergent effective time reversal symmetry, which is the time reversal symmetry plus some kind of mirror symmetry in the lattice. That time reversal symmetry squares to 1, not to -1. And of course, there's particle hole symmetry. So we are in the class BD1. And so that's a chiral class. And so typically chiral classes, so again, we can do this little trick where we try to understand these nodal phases by looking at family of 1D Hamiltonians tuned by some parameter. And so chiral, again, this is in a chiral class. There's what we can write Hamiltonian in this basis. And in 1D, these chiral classes are associated with the winding number. We can calculate. And so, yeah, okay. So here we're looking again at, let's say, this is just to show the location of the nodal points in this kind of spectrum here. And this is the calculation of this winding number. And what we see is that, you know, if we take, so again, we think about these family of 1D Hamiltonian as a function of ky. So if we fix ky right here, you see there's no winding of the phase. So I don't know if you can see this very clearly, but the phase goes from 0 to -pi, back to 0, up to pi, then back to 0. But if we part, for example, in this regime, then the phase winds along by 2pi in this direction. And if we kind of fix, you know, ky to be in this regime, we see that the phase winds twice in the opposite direction than here, by 4pi. Okay, so in that sense, we can really understand these nodal points as arising from this origin. Now, to another way of understanding, you know, or looking for signatures, let's say experimental signatures, is to think about now an open boundary system and just so start from the spin texture at the normal state. And so that already hints at the physics that we see here. So now we can, you know, again, so in this language, we can just think about this chemical potential, which is now tuned by our ky. And so if we now park our ky here, let's say, so in this regime, we're essentially in the limit of the famous Rashba wires by coworkers. And so in this case, indeed, what we have is just a 2-band Rashba-like model where the chemical, so we're basically populating only one of these bands. So this system, this 1D system is known to be associated with marijuana end states at the boundary. And so that would be topologically non-trivial. If instead we park our chemical or our ky here, we're in the trivial limit of the Rashba wires. So essentially we have 2 spin orbit coupled bands that are occupied. So that gives rise to two effective low energy K-type chains. However, they have an opposite chirality, meaning that the presence of the boundary would just couple them and they would gap up. So this would be a trivial phase. Now, if we move to this region between these pairs of nodal points, what we see that happens, it's a little bit hard to see because it's narrow, but the point is that if you notice the spin orientation of the middle band has flipped, right? And so what this corresponds to is now to 2 K-type chains, but this time with the same chirality, and those cannot be gapped the boundary. And so here we would expect to have, in this kind of effective 1D model, we would expect to have 2 stable marijuana modes, which are protected by time versus. And so this bulk boundary correspondence should be detectable in, for example, a Josephson-like current. And so again, if we focus on the different regimes, so this is just, again, showing what I was explaining now, just these boundary modes that appear when we take a finite system in one direction. And so these here, this corresponds to having 2 pairs of marijuana modes at the end. This is the one pair of marijuana modes at the 2 ends. And correspondingly, the current phase relation in a Josephson junction in these regimes show 4pi periodicity. Right? So these would be trivial, they have a 2pi periodicity, but in these regimes, we see a 4pi periodicity. Good. So Right, so that was all about Ising spin orbit effect, which is something that is due again to the lattice structure and is very strong. However, typical samples always have some kind of inversion breaking in the outer plane due to a substrate gauge, right? And so that should introduce Rashba spin orbit coupling, and the question is, how does this change the picture? And so if we add the Rashba spin orbit coupling, what we find is that the two symmetries that were protecting our BD1, or that was placing our system into the BD1 phase, are basically now broken. And so that leaves this effective effective family of Hamiltonians into class A, which has only one topological class, which is trivial. Hence, generally speaking, everything should be eliminated. However, there actually is an interesting situation which now depends on the orientation of the magnetic field in the plane. So far that orientation was not relevant, but when we add Rashba spin orbit coupling, there are special gamma M orientations of the magnetic field that leads to residual mirror symmetry in the system. And this, in fact, protects crystalline nodal topological phase. So only two pairs of these nodal points remain. They're also shifted away from zero energy, which is shown here by the white line. And so there's still a topological phase. It's, of course, much more fragile because it's now protected by crystalline symmetry. And we can, again, classify this based on topological invariance for this crystalline symmetry. So based on eigenvalues, this inversion symmetry. And what we find is that there's still a degenerate level here at this between these kind of remaining nodal points, which, as you can see clearly, are also shifted away from zero. Interestingly, this level is also now dispersive, so it's no longer flat. But since it's no longer a Majorana, no longer in a BDG phase, then this introduces a small, so this gaps up this 4 pi periodicity. We're back into 2 pi periodicity. Okay, so 10 minutes. Oh, that works well. Okay, so a couple of things which are interesting to consider now is first multi-layer structures, which I'll discuss a little bit. Importantly, this addition of Rashba spin orbit tells us essentially that there are ways to control topology now with these out-of-plane fields. So this is a very interesting idea to try to kind of leads to the possibility of creating devices, and of course how electron-electron interactions affect all this picture. And let me maybe very quickly tell you a little bit about multi-layer structures. So this was presented already for graphene. Essentially, we can do a very similar story now with these nodal topological phases. So we can think about a situation where we take these bilayers, orient them in the same way, not such that the Ising spin orbit operates in the same direction, and place them with a small twist angle between them, right? And so that kind of splits the pairs of Dirac nodes that arise from the different layers. And then those are kind of hybridized as well due to the tunneling between the layers. And that, again, very similar to graphene physics, introduces, so this hybridization, renormalizes these Fermi velocities. However, because we have a very large asymmetry between the two Dirac velocities in the different directions, that generally does not lead to a flattening of the band. Well, it's smooth, it kind of smoothen up the band, but it typically leads to formation of semi-Dirac points where different the different, if you wish, magic angles in different directions do not correspond. So, but that gives rise to all kinds of interesting physics due to some semi-Dirac effects. However, maybe more interestingly, and I should say that this was kind of also, it's very similar to what is known from stacking D-wave superconductors as well. But maybe more interesting than that is that if we have this twisted bilayer system and we apply a difference of phase between the two layers, so kind of in Josephson-like geometry between these two layers, that actually opens up a gap. And that gap ends up being topological. So this kind of drives the system into a topological superconducting phase, which now has chiral edge states. And again, this is somewhat like the situation for D-wave superconductors, which again was studied before. So importantly now, there's another, if you wish, tuning knob, even though it's a little bit less maybe accessible than just applying a field, but presumably now, by twisting these bilayers and applying some Josephson field, we can even gap them up and create topologically gapped superconducting phase. So that kind of leads me to the end. So just to conclude, so these kind of nodal superconducting phase should be characterized. So in terms of trying to detect this, this should be characterized by both having a flat bands at the edge, so that should be detectable, and by signatures of 4-pi periodicity in the current phase relation. Maybe more importantly, and which is actually a general feature of having gapless phases, is that you can actually tune them into gapped phases. And so ASHBA in this case just lifts the nodal points. In general, kind of completely destroys the nodal feature, but we end up finding the nodal crystalline phase depending on the directionality of the current. However, that is no longer associated with 4-pi periodicity. So this is, tuning the system between these two phases should be something one can detect. So importantly, we now have relatively simple, let's say, control of these phases by electrical control. And when we stack these superconducting phases, we can go into a topologically gapped phase. So that's another, if you wish, tuning parameter. And with that, I think your questions.
Thanks, very nice talk. If you would go from the monolayer to the multi-layer systems, nodal points would pick up nodal lines, like graphite, depending on stacking and so on. So now you would have Meidan, not Meidan, sorry, so kind of nodal lines of the conductor. And have you considered for there?
No, but it's a very interesting. Yeah, it's very interesting. Yeah, indeed, what you have is somehow a continuum, let's say, of nodal points.
Yeah, and then that depends on the stacking. How
of course, yeah. So all of this very much, yes.
Yeah. Yeah. Second question, if I may. Now, when you apply this field and you study the effect of with that, you also have like break time resolumetry and inversion system. So you could also study what happens to let's say anomalous space or the diode effect in the system. That would be another character.
We did not look into it, but yeah.
Any more questions? I'll have one. You were showing a two-dimensional Brillouin zone, but you were analyzing the data along with the fixed KY.
Yes.
And arguing that there's this sort of
why
are you allowed to do that? So where is it? 1 day is 1 day, 2 days 2 days. What is the what's the experiment? They can't just decide I'm making my experiment with the fixed KY, right?
Right. No, good point. So you're saying typically if I had an actual system and I do, you mean for the Josephson relation? This one, yeah. Right. No, so it's true. So okay, so of course, I'm taking a very theoretical view of Josephson function, which is in fact, I'm putting all this on a cylinder and etc. But well, first of all, if these junctions are long enough, and of course, the important issue is that they should be rather clean. But as long as that is the case, we can still it just kind of leads to contribution from all different Ks.
Okay.
And the point is that now, or there are 2 points, let's say. The point is that now when you have, let's say, this special orientation, which is, if you wish, it's like this zigzag orientation, except here it might be armchair, but never mind. Then you would have, you always have, so the actual current that you would measure, current phase relation would always have a 4 pi component.
So it always comes into the current phase relation.
Exactly.
When you have something in the K space that behavior, then
Exactly.
it kind of weighs into the current phase relation.
As long as, of course, as long as, you know, it's a smooth junction,
This
etc.
is a good quantum
Yes.
number.
Yeah. Exactly.
K is a good number.
And I should say that similar to the story with, you know, the zigzag edges in graphene, if you now have junctions that are not aligned, so I kind of align this in the best possible way. But if now I start aligning it more towards, let's say, the y direction, then actually what happens is that these regions shrink in K space. So that's another feature you could in principle detect, is that this 4 pi periodicity kind of goes, it depends on the orientation of your junctions. That's one thing. And again, with the idea is that with the Rashba spin orbit, you should kind of you should be able to remove it, because now it becomes again 2 pi periodic. So that's another, if you want, experimental model.
Marco?
Yes, about this twist graphene, there's some phase difference. So, so you end up to have a chiral superconducting photoparameter, so it breaks time versus
Sorry.
switching.
Yeah. First of all, yes.
How this is possible? Just
Well,
like
because
phase difference.
there's it's like a current. It's like just some current out.
You just put some current. Right?
Well, this is one way to make a phase difference, for example. So it corresponds to an effective breaking with the time versus.
But it's not just, it's not spontaneously induced chiral superconductivity.
No, that's a very interesting point, because indeed in D waves, so this is something we still didn't have time to look into. So there's 2 effects that was studied in D wave. Sorry, one is that there's a particular angle, indeed, at 45 degrees, I think, for D wave, is that where this is, as you say, spontaneously induced, which is even more interesting. But in fact, at any angle, when you add, so this is spontaneous, but if you add so if you add a phase difference, also in D wave, in any angle, you get this gapping up of the Dirac cones. And so this is rather similar to what was seen in the small twist angles. But yeah, it's a very interesting point to ask what would happen at, let's say, in this case, probably 30 degrees. Yeah.
Maybe. Okay. Regarding this relation, this is the energy aspect.
This is, yes.
Non-analytic at pi equals 0. What happens to the current? Because the current is the phase derivative.
Sorry, say again. You were talking.
If you take an absolute value of sine phi, usually you have a cosine phi here, but this is not analytic at pi equals 0. And the current actually is the phase derivative of energy. So then what happens to current at pi equals 0?
That is a good point. I need to check, because the point is that I was being a bit sloppy in the sense that this gap, it's always gapped at any angle, etc. But has a different, it has different dependence depending on whether your twist angle, how your twist angle compares essentially to this difference of phase. And so I'm not sure whether this one is the valid one for this one, but okay, then we can discuss. Yeah.